So transition-based parsing is the first and easiest approach to do dependency parsing. And this amazing scholar, you should read his articles. He's a very nice researcher and a teacher as well, very good teacher. And so from previous lecture, I said that we want to parse, for example, this sentence: economic news had little effect on financial markets. We want to produce such a dependency parsing. So we have set of parameters that we should learn. We have fixed parsing algorithm. Pick your algorithm. And then we have some constraint that for each paradigm, such as transition-based, we have a different set of constraints. Since most transition-based and graph-based systems do not make use of a formal grammar at all, Gamma will typically only restrict the possible dependency trees for a sentence to those that satisfy certain formal constraints. For example, the set of all projective trees. And what is a transition-based model? We are going to look at systems that parameterize the model over the transitions of an abstract machine for deriving dependency trees, where we learn to predict the next transition given the input and parse history, and where we predict the new trees using a greedy deterministic parsing. Of course, being a greedy, sometimes for, as I said, for long sentences, this transition-based model fails. For long sentences, it fails. Although in terms of computational complexities, linear is great, fantastic, but it fails for long sentences. That's why we need other approaches, such as graph-based approach, that I will cover in the next lecture. So what is the transition-based model? We have a buffer, we have a stack, and so sigma is a stack of words. We have a stack of words. And then we have beta is a buffer of words. We put words of the sentence in that. And A is a set of dependency arcs. So we connect word omega I to omega j via the relation R. So at the beginning of the algorithm, we put nothing in a stack except the root. And we put all of the words in the buffer, all of them in the buffer, and then we go on. So we have only 3 actions. So think about it like reinforcement learning. We have 3 actions only. It's finite number of actions. And the action left, it goes to the left. So adds the dependency arc to the arc set. So omega I is a word on top of the stack, like this, on top of the stack. And omega j is the first word in the buffer. This is the first word in the buffer. In addition, so after doing that, after going left, it pops up. So it goes out. We don't need it because we have already done with the dependency relation, so we don't need it. We just move on. And at the beginning, things we don't, and we have action right as well. It goes to the right. And we have shift as well. For example, at the beginning, when we don't have anything in stack, we just do shift. We don't have anything to do. So with an example, you will understand it's very easy. This shift reduce algorithm is very easy. At the beginning, as I said, only root is on the stack and everything is on the buffer. So the next transition is shift. The shift, economic shifts. It goes to the stack. And the next transition is left. News goes to the economic. News goes to the economic. Of course, we have learned this. We know that after learning, because we've already given the labels, so we don't need to worry about it. So we assume that we have learned this. So the next transition is left, so news and economic. The next transition is shift. There is nothing here, so just shift it. Just shift it. News goes to the stack. The next transition is left. Okay, we have two things in the stack, and we just shift it. And the next transition is left, going left. And then we pop up after that, as I said. The next transition is shift. So it goes, and we have a had. The next transition is shift again, had little. So we have this relationship. So at each state, we have some relationships. After, if you collect all of these things like this, you will see the dependency trees is extending more and more until it reaches the final dependency trees with all words covered. And then we go left. The next transition is left. The next transition is shift. The next transition is shift. The next transition is shift. The next transition is left. And then because it's left, we pop up. And finally, the next transition is right, going right. So from markets to financial, for on to markets, we go from left to right. So it's right. And so to doing this creates this relationship. So sometimes we go from left to right. And we go right. So we have two right thing. One from had to effect, the other one from on to markets. The next transition is right. The next transition is shift. We shift it because there is nothing in the stack. The next transition is right. We have had, we have, so finally, when root is on the buffer, then we are done. It means stop the algorithm. That's it. So this is the summary of the algorithm of what I've said. And the feature vectors for each configuration is really important. For example, it could be the top of the stack, one of the features, two top words on the buffer, another. You can create your own features. You don't need to be constrained to only these features. You can design your own features. So you could have hundreds of features because there are lots of things we can work on, combination of part of speech, the difference between them. Like in graph-based approaches, we have lot of features to deal with and to create. So we have lots of features for different C contexts and for different configuration. So for each configuration, at each configuration, we have a feature vector. So this is a vector, it's m-dimensional. For example, the first feature, the second feature, the mth feature. This is the mth feature. So for each configuration, we have a feature. And what do you want? In machine learning, we need features, because features, like for example, in image processing and computer vision, we use, for example, convolutions to create some features. Here, we use these things to create the features. And the labels are those things like that I will explain later. But there are two types of let's say feature type. One of them is address, the other one is attributes. And for example, address, you say the top of the stack, top two words on the buffer. And so this is the feature vector. And and these LDEP in the book, it means the top of the stack to the left, because this is the top of the stack, and this is the farthest child. Just read it as farthest child of the input, which is top of the stack, to the left. Or this one is farthest child of top of the stack, because this is top of the stack, to the right. Or this is farthest child of top of the buffer to the left. This is farthest child of top of the buffer to the right. And this is just for dependency label. And so we have attribute functions. We need this for to create features. And then we want to learn a classifier. These are your features and these are your labels. So you're done for learning. And we have only 3 actions: left arc, right arc, and shift. So we approximate the oracle by classifiers. In machine learning, we approximate it. We don't know it. Feature model, so you can say that, for example, some of them are of the type address, some of them are the type attribute. You can use lemma, part of speech. For example, in lemmatization. Lemmatization is different from stemming. Lemmatization. This is different from stemming. And you can use part of speech and many of these things for features. So we have training data. I mean the sentences and the corresponding trees. So in order to train a classifier for transition-based dependency parsing, we must therefore find a way to derive from D. And this is the training data. So we add D prime. We want to construct D prime given D. And finally, raise your words, not voice. It is rain that grows flowers, not thunder. We don't have any chatbot to create poetry, especially Persian poetry, which is very complex. But one day, chatbots can create some poems, beautiful poems, and some philosophical poems. And that's the beginning of intelligence.